So once again, good morning to all. Today's session we will be discussing different types of methods to find the frictional power of an engine. So before going to these methods, let's answer this question: what is friction power and how it arises? So already you know that friction power is the difference between indicated power and brake power. The indicated power is the power inside the engine, developed inside the engine, while brake power is the power comes through the crankshaft of the engine. It is a final power we are getting. So the difference of these two powers will be the frictional power. Frictional power is the sum of two quantities, that is friction loss and pumping loss. So you might have known what is friction loss is. As you know that there is too many components of the engine which are moving, so there will be always friction. The friction will be coming into play wherever there is relative movement. So that means between the piston and cylinder walls, between the piston rings and piston, and between the crankshaft, camshaft, bearings, valves, all the moving parts will be contributing friction. So this is known as the friction loss. And other than this, we have a loss incurred for driving the accessories. An engine have a lot of accessories. For example, a water pump in a radiator or a cooling system, we are using a water pump. Similarly, ignition system, we have a distributing arm which is rotating continuously. So for running all these accessories we require power. So this also contribute to the friction power. What is the pumping loss? To understand this concept, what is a pumping loss? So this is a figure of 4-stroke engine. You consider first stroke, suction stroke. You consider this. What is the pressure above and below the piston? See this. During suction stroke, that is piston is moving. Suction stroke, first one is the suction stroke. The piston is moving downward. The pressure above the piston is vacuum pressure. That means it is less than atmospheric pressure. But pressure below will be, that is at the crankcase, it will be almost atmospheric pressure. So that means during suction stroke, the piston is moving a low pressure region to high pressure region here. Similarly, during the exhaust stroke, what is the pressure above the piston? It will be greater than atmospheric pressure, and pressure below is almost atmospheric pressure. And here the piston has to move upward. So that means here also the piston is moving from a low pressure region to high pressure region. That is, during suction stroke, the gas pressure on the upper side is lesser than the lower side of the piston. Similarly, during exhaust stroke, the pressure on the upper side is greater than the lower side of the piston. In both these two cases, the piston has to move from a low pressure region to high pressure region. So for that, we might have to do or give some work to the piston. For moving any object from a low pressure region to high pressure region, we have to give some work, because naturally the objects will be moving from a high pressure region to low pressure region only. So this power we are giving, or this is known as the pumping loss. So that means the pumping loss represents the work to be spent for admitting the fresh charge during suction stroke and expelling the burned gas during the exhaust stroke. You can see this is actual PV diagram of an auto cycle, a petrol engine. So compared to theoretical PV diagram, we can see another loop in the bottom. At the bottom of this PV diagram, you can see a loop is there. So this loop represents pumping loop. This loop is known as pumping loop. So you can see at suction the pressure is less than atmospheric, and at exhaust the pressure is greater than atmospheric. This line is the atmospheric pressure. So the area between these two represents the work we have to give to the engine for running these two strokes. So that is the pumping power or pumping loss. Now what are the methods used to find the frictional power? Morse test. You might have heard this in the lab. Morse test is the first method. Retardation test. Then Willan's line method. Motoring test. Finally, we can directly obtain friction power by just subtracting indicate power and brake power if they are known quantities. So in this, these are the methods available for finding the frictional power. In this, the most important methods are the first two methods. From some point of view, the Morse test is most important, and similarly the retardation test also is very much important. We will be more concentrating on these two methods, Morse test and retardation test. Now what is Morse test? The main thing about Morse test is it is applicable only to the multi-cylinder engines. If our engine is a single cylinder engine, we cannot apply Morse test. And another advantage of Morse test is it calculates frictional power and indicate power without any elaborate equipment. So no additional equipment is required for this method. That is the important advantage of Morse test. Now let's check what is the procedure of Morse test is. Engine is first run at rated speed and at a constant particular load. So this is our first step. Do the engine run at rated speed? And first cylinder is cut out. So what do you mean by cut out? Whether we have to remove that cylinder? No. It is short circuiting the spark plug in SI engine. So first cylinder cutout means we have to short circuit the spark plug if it is an SI engine or a petrol engine. And we have to disconnect the fuel injector or block the fuel injector if it is a diesel engine or CA engine. So that is means we have to do this. If it's a petrol engine, we have to short the spark plug. If it is a diesel engine, we have to remove the injector or block the injector. That means the first cylinder will not be firing and it will become inoperative. For the first cylinder it will become non-operative. That means the first cylinder will not produce any indicated power. This is very important. We are cutting out the first cylinder. The first cylinder will not produce any power because firing is not takes place inside that first cylinder. But all the cylinders are connected to single crankshaft. That means the other cylinders will rotate the first piston inside the cylinder. So that means the frictional power will be there because all the parts are moving. So this important thing, we are cutting out the first cylinder and the indicate power stops, but it will be moving with the help of other two cylinders or remaining cylinders. So frictional power remains in the first cylinder. Now all that means other cylinders will motor the cutout cylinder. Now as a result, the speed will drop. First we are running this at rated speed. But now as we are cutting out first cylinder, naturally the speed will drop. So what we have to do is we have to bring back the speed to original rated speed by reducing the load. So we have to remove some load and bring back to the rated speed. So this is the procedure, and we have to repeat this for the remaining cylinders. We have 3 cylinders, we have to again connect first cylinder and cut off second cylinder, repeat the procedure, again connect the third and again run. So like that we have to repeat this procedure for all the cylinders. So this is a standard procedure for Morse test. It is very important. Now let's check how this find out the frictional power. Morse test, how Morse test, using Morse test we are going to find the frictional power. This is a 3-cylinder engine. You can see this is an inline 3-cylinder engine. This is our first cylinder, piston, second cylinder, third cylinder. So all are connected to a single crankshaft which is inline. So this is an inline 3-cylinder multi-cylinder engine. Now when all the cylinders are running, we are running all the cylinders at rated speed. What will be the equation of these three? This is, we are measuring the brake power. We are running all the cylinders at rated speed. So this BP total represents all the cylinders are running. We are measuring the brake power either through dynamometer or some arrangement. So brake power by running all the cylinders is BP total. Now BP total will be BP1 plus BP2 plus BP3. So BP total will be BP1. So BP1 is nothing but IP1 minus FP1, IP2 minus FP2 and IP3 minus FP3. So this represents first equation, the equation for running all the cylinders. Now we are cutting the first cylinder, we are cut offing the first cylinder. That means what will happen to the equation? Is it be same or is it be any difference? So that means the speed will reduce and we have to bring back the speed. We are changing the load. So that means we are reducing the load and this brake power will be reduced. So let's see, this is the brake power by cutting the first cylinder, BP1. So BP1 represents cutting the brake power by cutting the first cylinder. So here you can see indicated power becomes 0. The first cylinder we are cutting. So first cylinder we are cutting means the indicated power of first cylinder vanish. But friction power remains same because it is run with the help of cylinders. The friction power, the negative power will be there and remaining thing will be same. Second no change, third one also no change. So the only difference is in equation 2 the indicated power of first cylinder becomes 0. What will be the same equation when the second cylinder is cut off? Now we are connecting the first back and cut off second cylinder. So again speed will reduce. We are decreasing the load to make the rated speed. So again another brake power we will get. So that is second cylinder cut off. We are getting BP2. So what is BP2 equation? So here IP1 will be there because the first cylinder is again connected. But second cylinder is, see here the second cylinder we are cut off in second cylinder, no firing takes place. So indicated power will be 0, IP2 will be 0. And other things are same. So equation 3, the only difference is IP2 vanish, no power generated in the second cylinder and other things are same. So again this is repeated for third cylinder. So we have 3 cylinders. We have to do the same procedure for all the cylinders. So again third cylinder is cut off. What is equation? Yes. The only difference is now IP3 vanish. No indicated power in the third cylinder. It becomes 0. Frictional power is there and other things are same. So thus we are getting 4 equations. First one is running all the cylinders, more brake power is obtained. Second one, we are cut off first cylinder, so another reduced brake power is obtained. And again we are doing the same procedure. So we are getting 4 different brake powers. So this we can measure using a dynamometer. What are the numerical quantities of these brake powers? Now to find out frictional power using this 4 equation, it's very easy. You just subtract equation 2 from 1. So subtract 2 from 1, what we will get? That is BP total minus BP1. BP total, this has some numerical value. So BP total minus BP1. So right hand side, what will be remaining? Yes. So right hand side only IP1 will be there. So that means subtracting 2 from 1, we will get IP1. Similarly, if you subtract 3 from 1, now subtract 3 from 1, so that means BP total minus BP2, and on the right side we will get IP2. So similarly, again subtracting 4 from 1, we will get IP3. So we are obtained IP1, IP2, IP3, all the indicated power by using these 4 equations. Now if you add all these 3, you will get the total indicated power of this engine. So just add all this, you will get the total indicated power. But you want frictional power, so already you have total indicated power, and initially you have obtained the total brake power of all the 3 cylinders. So here you have already obtained total brake power. Here you have obtained the total indicated power. So just subtract IP total and BP total, you will get the frictional power. So this is the procedure for finding the frictional power using Morse test. So just memorize these equations. Numerical problems will be asked based on this. So if it is a 4-cylinder engine, you have to add one more equation. So like that you can easily get total frictional power of the engines. What is retardation test? As the name suggests, retardation test involves retarding the engine, that is reducing the speed by cutting the fuel supply. So what is the procedure for retardation test? So here also the first engine is made to run at rated speed but at no load. So that is important. Here we are running the engine at rated speed, but it is at no load and rated speed, and a steady state condition is achieved. So after that we will be completely cut off the fuel supply and the engine will stop. If you are cutting off the fuel supply to 0, engine will stop, and the time taken for that speed drop. So the speed will be dropping to 80%, 60%, 40%. So you have to just note the time with the help of a stopwatch. You have to measure the time taken for reducing the speed to 0. Now this same procedure is repeated at half load also. So half load you have to run at rated speed, then fuel is cut off, again the speed will fall. You have to note down the time for a particular speed reduction. So we are doing this no load and the half load. Now a graph is plotted where in the x-axis we will plot the speed. So x-axis we are plotting speed and y-axis we are plotting x-axis we will be plotting speed and y-axis we will be plotting the time. So the y-axis we will plot speed and the x-axis we will plot the time. So we will be having two plots because we are running half load and no load. We will be having two plots. This is the plot obtained. So this is a plot obtained. What you can see is time we are plotting time in the x-axis, speed in the y-axis. So at first no load. So this point represents the rated speed. So this line, see this line horizontal line represents the rated speed. So at no load and rated speed we are cutting off the fuel. Speed reduces to another 100 rpm less. Suppose this is rated speed is 1500. Now we are reaching 1400. So what is the time for that? That is T2. Similarly, the same speed reduction, that is rated speed 1500 to 1400 at half load, we will be taking only T3 time. So it is common sense that half load the speed reduction will be more faster compared to the no load. So T2 will be obviously greater than T3. So just understand this, we are plotting speed versus time and just take any two speed. So from rated speed, here we are taking the first as rated speed, 200 rpm lesser speed. What is the time in each case? We already know the equation. Torque is moment of inertia into angular acceleration. So T is equal to I into d omega by dt. So T is torque, I is the moment of inertia, so omega is angular velocity, so angular acceleration is d omega by dt. Now what is I? Moment of inertia will be mass into radius of gyration, mk square. So these are standard equations. Now you rearrange, substitute 1 and 2 together and rearrange, we will get d omega is t by mk square into dt. So this is a differential equation. Now you integrate, we are changing speed from one speed to 1, 2 to 1 and we are getting two time levels. So integrating the above equation to two speeds, any two speeds, we will be getting an equation like this. Differentiating or integrating, we will get omega 2 minus omega 1. Omega 2 minus omega 1 is equal to t by mk square into t2 minus t1. So this is the equation we are getting after integrating this differential equation to two different speeds. Now you should substitute these two cases. So what will be the torque at no load? So no load, there is no load. So that means only frictional torque will be there. So here we are splitting the torque into two categories. One is torque due to friction, other one is torque due to load. So at no load, the only torque available is friction torque. The only torque is friction torque. But at full load or half load, the torque will be friction torque and load torque. Two parameters are there, TL and TF. So we have to substitute this equation 5. So first take at no load condition, this is no load. No load, the torque is only TF and time taken is, with respect to this figure, the time taken in changing speed from omega 2 to omega 1 will be T2. So just substitute that, we will be getting omega 2 minus omega 1, that is the speed difference, equals to Tf by mk square into T2. Similarly, you have to substitute for the half load. So here what is the difference? Yes, here the half load, same equation, but two differences are there. That is, here the torque will be TL plus TF because load is also there. Total torque will be frictional torque plus load torque. And time changes. So you can see time for this speed reduction is T3. So speed reduction from here to here, half load is T3. Now we have equation 6 and 7. The left hand side is same. So obviously right hand side also should equal. So equate the right hand side and we have some common terms. Mk square, we can cancel that. So equating the right hand side and rearranging, we will get TL plus TF into T3 is equal to TF into T2. Again simplifying, that is dividing throughout by TF and rearranging, we will get TL by TF is equal to T2 by T3 minus 1, or TF is nothing but TL into T3 into T2 minus T3. So this is our equation. We are obtaining the torque due to friction. So TL we can measure with the help of dynamometer. We can measure the torque due to load, and this time we are measured using a stopwatch T2 and T3. So thus we can find out TF. How to find the friction power? Yes, basic equation 2 pi nt by 60. So the friction power is 2 pi ntf by 60. So this is the equation for finding the friction power through retardation test. Our next method is Willan's line method. You might have done this in your lab. Here a graph between fuel consumption and brake power is plotted at constant speed. So fuel consumption in y-axis, brake power in x-axis. And we have to fit a straight line. If you have 6 points or 6 readings or whatever it is, we have to fit a straight line in this data and extrapolate to meet the negative x-axis. Then this negative intercept of x-axis will be the frictional power. And this method is also known as fuel rate extrapolation method. So let's see how this is done. So you can see here this is data obtained from some experiment of some engine. So here we are plotting the fuel consumption in gram per second or whatever it is in the y-axis, and corresponding brake power in kilowatt in x-axis. So you will get a number of points. You fit a straight line. So you can see here at point A, this point, the brake power is 0, but fuel is consumed, some amount of fuel. Here it is around 0.3. So at point A, even though the brake power is 0, the engine consumes some fuel. So it is for you overcoming the frictional power. So that means if you further extend this line to the negative x-axis, and at point B, where the fuel consumption is 0, a negative power we are obtaining. So that will be obviously frictional power. So that is the concept of Willan's line method. At point B, when the fuel consumption is 0, this negative power will be frictional power. So that is the concept of this Willan's line method. What are the limitations? This is only a graphical method, so it is having some limitation. First one is it hold only for a particular speed. So we are doing the experiment for a constant speed. So this method, the friction power will be only for that speed only. Second method is applicable only to CI engine, because SI engine we cannot be make fuel consumption into zero, because already air fuel mixture will be entering, so that concept will not hold for SI engine. So this is applicable only to diesel engine or CI engine. And main drawback of this method is very low loads. This plot will not be linear, so it will have some non-linear nature, and if you fit a straight line there is a chance of errors. So if it is not at all linear, we will not be able to get a good straight line, and this intercept will be wrong. So that is the main drawback of Willan's line method. At low load this method will not hold good. Our last method is motoring test. So as the name suggests, we are motoring the engine, or we are running the engine by giving power to the engine. Now how the procedure is: here the engine is operated at rated speed and steady state conditions for a particular time, and here we require a particular dynamometer, that is swinging field type electric dynamometer. So here we using swimming field type electric dynamometer, and it will absorb the power during the initial running. And the ignition is cut off by shorting the spark plug or by blocking the fuel injector. We are stopping the ignition, and by electric switching device we can change this dynamometer into running as a motor. So initially the dynamometer absorbs power from the engine, then it reverse, electrical circuit reverse, and it will run as a motor. So it will give energy to the engine for running, because we are cutting off the engine. Now firing is not there, the engine will be going to stop, but then we are setting the dynamometer and we will be running it as a motor, and this motor will crank the engine at the same speed. Now you know this is the frictional power, because there is no indicated power. We are firing is not there, no indicated power in this engine, but we are simply running the engine by rotating with the help of this dynamometer. So that power, if you measure the power supply from the dynamometer to the engine, it will be the frictional power. So that is the concept. We are motoring the engine with the help of a dynamometer when firing is stopped, and that power will be the frictional power. The main advantage of this method is we can find the frictional power from each element of the engine. That is, if we want what is the frictional power by piston or frictional power by another moving device, etc., we can find out by this method. How? By progressive stripping of the engine. So that means, progressive stripping means first the engine is run with all the components, then we can remove some components and do the motoring. So we will get another power, frictional power. So the difference will be the frictional power due to that component. So like that, the main advantage of motoring test is we can find the frictional power contributed by each and every component or moving parts by this progressive stripping of the engine. The limitation is, but the temperature and pressure of this engine will be different from a real engine, because firing is not takes place. So that is the limitation. We are doing this experiment by without firing, and we are calculating frictional power, but that will be somewhat different, because in an actual engine when firing takes place the temperature and pressure will be very high. So that is the main limitation of this method. So with this we are concluding this session. Thank you all.